you excite your absorbate to some excited state, and depending on what you excited, this excited state can decay, can leave like that, can give you an ion, and the ion can then re-neutralize, and you get picked up by the mass spec. Okay, so you have excitation to a repulsive ionic state in this case, and then re-neutralization. That's the model for ESP. You can also do like this. You can. So this is the original picture that you have, depending on where you go on the excitation curve. You can also excite to a metastable state, A star here, and then it dissolves as a neutral. Here it comes off the surface as a ion, and then re-neutralization. If you go to a metastable state, it will leave the surface. M here is my surface, A is my absorbate. A as A star, and A star is the excited absorbate, and you can somehow pick that up. Okay, so it's the same concept. You have excitation followed by neutralization if you have an ionic state. If not, you just detect it normally by mass spec. And photon simulated desorption is the same way. Essentially, you have the photon energy. You scan your photon energy, right? Remember, you have to have a way to scan this kind of light spectroscopy. You have to scan your wavelength of your photon energy, and then measure total pressure. So this is the total pressure that you got, and then you take the derivative, you get peaks like this, right? Derivative of this to give this, and then the location of that tell you the electronic state, right? Because these peak desorption, when you hit a state, it will tell you a upper state that you got. So it gives you a little bit more information about the electronic structure in some way of your absorbate as you excite the molecule. Not exactly quite the same as TP, temperature coefficient desorption, because here in temperature coefficient desorption you are really doing chemistry, thermochemistry, whereas here you're doing just the electronic excitation, and that is a physical process. It's an electronic de-excitation process to give you this desorbate. Physics is a little bit different. Okay, so that's it. In the remaining half an hour or so, I'd like to tell you a little bit about surface chemical process on this, and it's very descriptive, so I can go rather quickly. It's a classification scheme, but I think it's important because you may see this later on as you move to pursue a career. You may hear about some of these type of reactions that occur on the surface, and I classify them generally as three types of reaction, perhaps a little bit different from others, in an industrial way. Think of it in an industrial point of view. The first one is, of course, corrosion reaction that you see on a daily basis. So the corrosion reaction, the material interact from the gas in the gas phase will produce some product with the surface, right? And oftentimes you can think of this as an etching reaction. Okay, so the etching reaction is that the gas come onto your surface and slowly eat away your surface. Okay, so the reaction, for example, a classic example is chlorine gas reacting with your nickel surface, right, and form nickel chloride, which is a gas, and then this gas leaves the surface. So with time, your nickel surface it gets corroded away, meaning that you are eating your nickel surface, reducing in mass. The other one is a classic oxidation reaction, right? Both of these are oxidation reaction of the carbon with water. Water provides the oxygen. You get your CO and H2. Molybdenum is a solid, once again. Oxygen comes in, give you moly oxide, trioxide, and that is a gas, and that leaves the surface. So your moly solid is even up, get etching. This is called etching reaction, chemically etch, right? This is chemically etch, and this is part of course, a classic corrosion reaction. The other classic corrosion reaction is that you actually have layer formation. Your product is not gaseous anymore. Your product is actually non-volatile, and you got deposited on there. So the good example, of course, is rust formation. Your oxygen reacting with iron and get you Fe2O3 and Fe3O4 and things like that. And that is a rust formation, and the rust the oxide stay on your surface, and the nature of your surface changes because of this rust formation. The second type that I talk about is crystal growth reaction. Again, from the so this is I'm thinking in terms of car industry here, right? So the car, you have rust formation. Here I'm thinking about semiconductor industry here, that crystal growth reaction, whereby you can create this layer, computer industry, you know, your Pentium chips and so forth, that you will require growing some crystal material, particularly silicon in this case. So the material is deposited onto the surface in a controlled way, right? In a controlled way, without a decomposition reaction, in order to form a surface, or to extend this surface, build up this material layer by layer, okay? And much of these are being used in semiconductor industry, and recently nanostructure material, right? Like fuel cell is a battery material. You're growing this layer by layer in a controlled way. And I'll give you 3 examples. One of the most important one is physical vapor deposition. Physical vapor means that you just evaporate something by some means. You can do it by heat, right? By thermal evaporation. You can do it by electron beam, heating an electron beam to a material like silver, for example, and then turn it into gas, right? First, you can start with your source, right? Your source, which is your material, or sometimes we call it target. You turn your target, usually is a solid form, into wafer form. So if my source is silver, target is a disc or foil or something like that, I heat it up into somehow, and I can do it by heat, by electron beam, or by other means. It generates a vapor of these silver atoms, and then I expose this silver vapor onto my substrate, right? And this silver vapor would then condense in a controlled way. I say controlled condensation to become silver solid. Okay, and this silver solid can be a film, and this film can be amorphous or can be crystalline, depending on how good. There's a lot of physics involved between the lattice matching between the substrate and the thing that you want to quote, right? That you want to deposit your gas here. Do they have a similar lattice parameter? If they have similar lattice parameter, then you have epitaxial growth, that it will grow in a crystalline format. If you don't, then it may grow in a random format, and you have amorphous form. So there's a lot of technology involved in this film growth technique. Is part of the film growth technique, physical vapor deposition. And the more recent introduction to this in terms of thermal evaporation, you can use a laser beam to do this pulse laser deposition. And this is an example of one of the systems we have in our lab, that you use an XM laser, fire at the laser at the target, and then your plume, this laser plume, which contains the vapor that you got. So this vapor, composition of vapor is really complex, because you could have iron or electron or neutral in here, and your substrate is on top. Okay, it's a different view down here that you can see the little silicon chip that you got, and you just coat it. And this is another way of physical vapor deposition. This is in the early days. Why you need a laser? Well, because some material, ceramic material, oxide, complex oxide material, has a very high boiling point, and it's not so easy to just use thermal technique like a little hidden filament or electron beam to heat this thing up. So a laser gives you a dose of energy, and that allows you to vaporize this material. And this is a common technique that people use to make